For any assignment-related queries, call us at +1 678 648 4277. You can mail us at support@mathhomeworksolver.com or reach us at https://www.mathhomeworksolver.com. 1a. A direct complement to a subspace L1 in a finite dimensional space L is a subspace L2L, such that L equals L1 L2. Prove that for any subspace L1 a direct complement exists, and the dimensions of any two direct complements of L1 in L coincide. B. For a linear map F, Lm, let Coker F be a direct complement of IMF in M. Define the index of the map F by INDF equals dim, Coker F, minus dim, kerf. Check using A. that INDF is well defined. Prove that if L and M are finite dimensional, INDF depends only on the dimensions of L and M. INDF equals dim, M, minus dim, L. Problems. C. Set dim, M equals dim, L equals N. What can you deduce from B about systems of n linear equations in n variables? 2. Two ordered tuples of subspaces L1, L2, Ln and L1, L2. Ln in a finite dimensional L are identically arranged if there exists a linear automorphism, bijective linear map from a space to itself, F, LL such that F, Li, equals for all Li equals 1, n. Show that I all triples of non-coplanar, pairwise distinct lines through 0 in R3 are identically arranged. Classify the arrangements of quadruples of such lines in R3. mathhomeworksolver.com. Solution. 1a. Given a finite dimensional linear space L and a subspace L1 subset of L, we want to prove that there exists a subspace L2 subset of L, such that L1 circled plus L2 equals L. Furthermore, we want to prove that the dimensions of all such direct complements to L1 coincide. Let dim L equals L. We pick a basis, ei, L1 for L1 and note that I equals 1 dim L1 equals L1. We then use the basis extension theorem and extend the basis of L1 to the basis of L. Thus, E1, L1, L1 plus 1, L, spans LL. Let L2 equals span, ei, I equals L1 plus 1. Since L1 intersection L2 equals 0 and L1 plus L2 equals L, we note that L2 is a direct complement to L1. Furthermore, dim L2 equals L minus L1. 2. Let L2 be a direct complement to L1 and ei, L equals 1 be a basis for L2. We extend the basis of L to L by using the basis vectors of L1. Thus, 2 1 E1, L1 spans L. Hence, it must be that dim L, EL2 is equal to 2L minus L1. However, this is the same as dim L2. Thus, dimensions of all direct complements of L1 coincide. B. Given F, Lm, we first show that INDF equals dim, Coker F, minus dim, Ker F is well defined. We note that since part A defined direct complement only for finite dimensional spaces, we restrict our attention to a finite dimensional M. Using the result from part A, we find that Coker F, a direct complement to M F subset of M, always exists and has a finite dimension. Furthermore, Ker F also always exists and has a well-defined dimension. We can then take dim Coker F equals C and dim Ker F equals K. Hence, INDF equals C minus K. We note that C is always a non-negative integer and K can be either a non-negative integer or infinity depending on the dimension of L. Thus, INDF is well defined. For finite dimensional M and L, let dim M equals M and dim M F equals I. Then dim Coker F equals M minus I. Further, let dim L equals L. Then dim Ker F equals dim L minus dim M F equals L minus I. Thus, INDF equals M minus I minus L minus I equals M minus L equals dim M minus dim L. mathhomeworksolver.com C. If dim m equals dim l equals n. Then ind f equals 0 and also dim coker f equals dim cur f. If cur f equals 0, then also coker f equals 0, and the system of linear equations always has a solution, while the system with a 0 r.h.s has no non-trivial solution. Problem 2. Solution: we want to show that all triples of non-coplanar, pairwise distinct lines through 0 in R3 are identically arranged. Let E1, E2, E3 be a basis for R3, and let 6 equals a 1 IE1 plus a 2 IE2 plus a 3 IE3 for I equals 1, 2, 3 be direction vectors for 3 non-coplanar pairwise distinct lines in R3. Further, let V equals a 1 IE1 plus a I2 IE2 plus a 3 IE3 for I equals 1, 2, 3 be the direction vectors for a second set of non-coplanar pairwise distinct lines in R3. For 6 and 6 to be identically arranged, we must find a linear map F such that F, 6, equals V for I equals 1, 2, 3. This is equivalent to I finding a matrix T such that T, age, equals age. Since the three lines are linearly independent, we can invert the matrix of coefficients. Thus, T equals Aij, age, minus 1 and 3 such lines are identically arranged. To consider the arrangements of 4 such lines, we note that direction vectors for 3 such lines span R3, and thus we express the direction vector for the fourth line as a linear combination of the first 3. Namely, V4 equals 1V plus B3 V3 B1 V1 plus B2 V2 plus B3 V3, and V4 equals B1 2 V2 plus B. Further, T V4 equals B1 T V1 plus B2 T V2 plus B3 T V3. Hence, if we add a scaling factor to the first 3 direction vectors T, 6 equals BBII6 for I equals 1, 2, 3, it follows that T V4 equals V, and thus all 4 quadruples of such lines are identically arranged. MathHomeworkSolver.com